Good evening, everyone. I want to talk to you this evening because there was a sort of a mathematical bloodbath at City Tutoring this morning, and it had to do with the rational roots theorem and the fundamental theorem of algebra. But before I even get into that, I want to send out a message to the young man. You know who you are. You wrote to me a beautiful letter that I received yesterday, Friday, and it was such a blessing to receive your letter. And you said that you're 14 years old and you are in Ohio. The letter that you wrote to me is absolutely well written. It is beautiful, actually. And I wrote you a letter today, Saturday. I penned a letter with my old pen, and you should be receiving your letter next week. I actually went because I happened to be in the area. I went to the post office today and I delivered it. I handed it over to the postman personally. I made sure that it's going to, I asked him, I said, how long is it going to take for the letter to get to you? He said about between 2 and 5 business days, depending. The Lynchburg, Virginia mail is very slow. We are sort of in a, not completely isolated, but we're not always in the hub of things. But I wrote you a handwritten letter, and I very much feel blessed that you have written to me. So thank you for that. I hope we keep the correspondence going. By the way, all of you are welcome to write to me. If I know that you took the time to write a letter to me, I will make sure to write you a letter. And I use a very old pen from the 19th century, actually. I prefer writing with these pens because I use script. Although for the young man, I didn't use script in the letter because I wasn't sure if you were able to read script, because I know in some schools they don't teach it anymore. And so I printed it out. I printed out the letters I wrote. And but anyway, I never buy pens because I have this one. Why would I buy any other pen? And I use the ink. All I have to do is buy ink, which lasts me for a while. So all I have to do is it's dip and just write along. But anyway, I really wanted to talk to you tonight about the rational roots theorem and just I'm going to share with you the rigorous classwork that we did this morning. Every Saturday at City Tutoring, we have a math boot camp, and we have young people come. I was leading a group this morning of 10th graders who are very ambitious, and they were shocked, they were horrified at their lack of preparation. There was a time long before this era of handheld distractions and pedagogical decay, when young scholars of mathematics were entrusted with they had a sacred duty to think, to reason, to prove. And yet, I stand before you today and I am aghast as the rational roots theorem and the fundamental theorem of algebra teeter on the brink of obscurity. They have become casualties of an age that is more enamored with computational shortcuts than intellectual rigor. We see it in the comments. In fact, one of my famous videos, when I was discussing how an honors Algebra 2 student failed the examination, I had one person who wrote to me the silliest comment I've read in this month. He said, why is this test so hard? He said they don't ask these questions. I don't know who they is, by the way. Certainly we do. We ask our students. Our students are capable, sir, if you're watching this video. And he said, oh, there's no need to be so rigorous. Absolutely ridiculous that we have people who think that way in America these days, that they don't want to test. Can you imagine that? What kind of I don't know if he's a father, I don't know if he's a teacher, I don't know what he is. But what kind of man says that? What kind of person, man or woman, says that they don't want to ask our students rigorous questions? We have, in our infinite folly, we've replaced the chisel of logical deduction with the sledgehammer of brute calculation and ignorance. We have deemed it sufficient that students press buttons on plastic devices made in China, rather than wrestle with the eternal truths of numbers. We have the rational roots theorem, the very key to unlocking the nature of polynomial roots. And from what I saw this morning, it has been abandoned in favor of trial and error, as though mathematics were a mere parlor game. And the fundamental theorem of algebra, that grand proclamation that every non-constant polynomial equation must have a root, we have cast it aside as though it were an antiquated superstition rather than the very foundation upon which modern algebraic reasoning is built. But I challenge you, I ask you, what, pray tell, remains of a civilization that neglects its intellectual inheritance? Can you have a house stand when its beams are left to rot? Can a bridge hold firm when its cables fray? No. And so we have the edifice of mathematical education crumbling before our eyes, when students are deprived of the very tools that sharpen their minds. We are raising generations who know neither the satisfaction of a well-constructed proof nor the joy of a theorem well understood. We hand them machines to do their thinking and then feign surprise when they can think no more. In fact, we have entire generations of students who don't think, and even adults too. What shall we say, assuming we have a future generation? At the rate things are going, I don't think we have a future. But I will not participate. I will not have city tutoring participate in the decay and in the lack of standards that we are seeing in so many of our schools. And if you are the type of person to tell me, oh, it's not necessary, why be so hard? Then that tells me a lot about the type of person you are. You know, the kind of person you are is that your character is revealed by what it takes to stop you. That's not my phrase. That dates back centuries. The measure of your character is what it takes to stop you. It's an old phrase, but it's very true. And if you are the type of person that quakes when you are challenged, you don't have what it takes to build a civilization. You're not civilized yourself. And so we need to go back to these rigorous foundations. And what I'm going to do in this video is I'm going to share with you the document, the sheet of the classwork that we did this morning and the lesson, so that all of you, and you can let me know in the comments, but would it be bold of me to say that your teachers are not teaching you this? That you are not learning at school the rational roots theorem and the fundamental theorem of algebra? Let me know. I might be wrong, but that's all of my students this morning said we do not cover that in the school. Now, of course, I am in an area. I am in Virginia. I am in Lynchburg, Virginia area. So your mileage may vary. Public schools here don't have it. In fact, just the other day, there was a controversy because in our city council, because I don't want to give out any names, but you can look it up if you want. One of our city councilmen was saying that the teachers in our schools, in our public schools here, that we pay taxes for, by the way, are more concerned with disseminating, just the craziest ideologies rather than teaching our students. That was, and then the teachers were all offended. They were outraged at this. But those are the facts. And I haven't been to a city council meeting recently, but I will be. I do plan on going to a few because I don't want my tax dollars to be going to some of these schools. Some of these schools are not doing what they're supposed to do. So your district might be different. Your district might actually teach this. And I've had students online, and they also tell me that their teachers don't cover that. In fact, I've had teachers tell me that there's no reason. Can you believe that a math teacher? How can you call yourself a math teacher and say there's no reason to teach the rational roots theorem? That's ridiculous. So anyway, I'm going to show you what the rational roots theorem is and how it relates to the other topics like the fundamental theorem of algebra and all that good stuff. So stay tuned, because tonight you're going to be learning a lot of new things, most of you, and I think it's going to be useful for you. But the main thing is, let us not be complicit in this great crime against reason and against mathematics, education. Let us restore what has been lost, demand that rigor return to its rightful throne, and ensure that mathematics remains what it has always been: the pursuit of truth, unmarred by mediocrity, untainted by indolence. All right, so this is the rational roots theorem. Let me get rid of some of this mess from the earlier class. I want you to have a look at it, and we're going to talk about it. If P and Q denote integers and Q is not equal to 0, obviously, such that P over Q is in lowest terms and represents a rational root of a polynomial equation in simple form with integral coefficients, then P must be an integral factor of the constant term and Q an integral factor of the leading coefficient in the equation. Now, a couple things. Yes, it is true that you should only use the rational root theorem when the coefficients are small, and really as a last resort, when when your instructor tells you to. It's really less efficient than some of the other steps you could take first, but it is still a mathematical principle that you should know. You can also factor, if you can, you should try factoring as much as possible, because it might turn out that perhaps you don't need the method if you can simplify a polynomial of a higher order, perhaps like x to the third or x to the fourth, and you can sometimes reduce it to a combination of lower order equations. So there's no need to use the theorem if you can do that. However, just for the sake of argument, let's do a little example here. Let's say you had x squared equals 2. Well, if I move the 2 to the left side, I have x squared minus 2 equals 0. I have a quadratic form of some kind. Now, the constant term here is negative 2. So remember what it says in the theorem. We have P over Q. P is the factor of the integral factor of the constant term. So already P is going to be negative 2. And then it says Q is an integral factor of the leading coefficient in the equation. Well, that's going to be negative 2 over 1. So what does that mean? That means that if you take negative 2 over 1, then the factors of P are going to be P. If you write, this is why we do set theory. Now you see why it's used. That's going to be P is an element of. The factors are going to be 1 over negative 1, negative 1, and also 2 and negative 2. And likewise for Q, the elements of Q sorry about that. I'm going to put it up here since I don't have room. It's going to be 1 and negative 1. So what does that mean? It means that the only rational numbers to test here as roots are these four integers here. So if we go back to the original equation, if we plug in these values, notice what's going to happen. I want you to plug in those values for x. And notice what happens. If we test 1 and negative 1, we actually get 1 is equal to 2. Contradiction. False. If we plug in 2 or negative 2, you now get that 4 equals 2. Also a contradiction and false. So what do we do from there? Well, if we go back to the original example, we said that x squared equals 2. You know that if you were to solve this as an equation, you would take the square root of 2. And that means that this example here is going to be the square root of 2 and negative 2, negative square root of 2. And it has no rational roots. This equation has no rational roots. They are irrational. You should know by now that square root of 2 is going to be irrational. So, what about the proof of the theorem? How would we prove that? Very important to do proofs. So, if we let P and Q, we're saying that those have to be integers, and we said Q cannot be equal to 0. So that P over Q is in lowest terms. So, if we're saying that P over Q is a root of the equation, sorry for my handwriting, I'm just not on the best surface. And what equation is it going to be? We're going to have A over times P over Q, and that's going to be raised to something, right? Let's say to the third, plus B to the P over Q, that's going to be squared, plus C, and then P over Q, plus D. And all of that should be equal to 0, by the way. I just don't have room to write it on there. But you get what I mean. I hope you're writing it down. So now we have fractions here, don't we? So you want to multiply by, you always want to get rid of your denominators here. So you could multiply each member, these are called members of the expression, of the equation, by Q to the third. And if you multiply everything by Q to the third, you now have AP to the third. And then you have BP squared Q. And you also have CPQ squared. And DQ to the third equals 0. Now, you can apply negative dq to the third to each member. In other words, subtract it from each member. And if that's the case, you are left with AP to the third plus BP squared Q plus CPQ squared equals negative dq to the third. And now if you substitute on the right side, you can substitute D times negative Q to the third and see what happens when you do that. I want you to pause the video and see what happens. So this is what your expressions look like. When you substitute negative Q to the third on the right side, and you also do, we're going to show P, we have to show P as a factor of the left member here. Now, notice that Q and negative Q to the third have the same prime factors. Why? And if P and Q have 1 as their greatest common factor, why is that? So we have P and negative Q to the third. They have no integral factors in common except 1 and negative 1. And also, you should know by now that because sums and products of integers are integers, we have the left and the right members of the equation. We have integers here. So that means P is an integral factor of the left member, and it's also a factor of the right member here, D times negative Q to the third. And so that means that it must be an integral factor of D. And so that means that P is going to be an element of the integral factors of D. And now we just have to, basically, to complete the proof, we have to transform the, I'm going to circle it in red, this. We have to transform that. So if we take out Q, then we have BP squared, and that's going to be, let's see here, CP cubed plus DQ squared. And that's going to be, of course, A times negative P to the third. And there you have the proof. Now we're going to use it in, I'm going to show you the classwork for our students so you could see some of the work that they were doing this morning. All right, have a look at number 3. Have a look at number 3. I don't know if you could see it well on your screens here. I've asked them this morning to find all zeros of the polynomial function, which was x to the third plus 7x squared plus 16x plus 12. So here is an example of you can actually use the rational roots theorem. And you use factors. The constant term here is 12. And we divide it by the coefficient. The leading coefficient here is 1. So we really have 12 over 1, which is 12. And these are the factors, of course, of 12. Well, we could go actually write it out neater. So the factors would be, of course, plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, and 12. Plus or minus, by the way. I'm just not putting the plus or minus for sake of room. But it should be plus or minus. Now, how do you deal with this? You can use synthetic division. You can test using synthetic division. If the remainder is not 0, then it means it is not a root. It is not a root. And so in this case, the 2 actually worked. And because the 2 worked, we have -2 and 3, and -3 as well. So that's one example of what they did this morning. This is one application where you can easily use the rational roots theorem. When they want you to find the zeros of the polynomial function, in this case, you do have a reduced 12 over 1, just like with number 4. It would be 4 over 1. And then you would evaluate it the same way. I've also talked to them this morning about this, the fundamental theorem of algebra. How many of you, let me know in the comment sections, how many of you have gone over this in Algebra 2? Algebra 2, the fundamental theorem of algebra. I gave them a little table here. Notice that there's a relationship between the degree of a polynomial and the number of solutions of f of x equals 0. And it was first proven, that kind of generalized, the relationship was proven by the German mathematician. Back in those days, Germany did good things. Carl Friedrich Gauss. And the fundamental theorem of algebra is here. If f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And the corollary, of course, is that if f of x is a polynomial of degree n, and n has to be greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions. Each solution repeated 3 times is counted as 3 solutions, and so on. You recall, perhaps, you might recall from your studies of complex numbers, by the way, the conjugate pairs. Remember that the conjugate pairs also count. So what I'm getting at is you recall from your study of algebra, hopefully, that when you're dealing with imaginary roots of a quadratic equation, you have those conjugate pairs. So that means that you have 1 minus 3i, and therefore 1 plus 3i is also a solution as well. Just something to keep in mind. We also went over with them where was it here? I had it somewhere. There we go. Descartes' rule of signs. Let me know in the comment section if you have gone over this at school. The rule of signs. And basically what it says is the number of positive real zeros of f is equal to the number of changes in sign of the coefficients of f of x, or is less than this by an even number. And we also said that the number of negative real zeros of f is equal to the number of changes in sign of the coefficients of f of negative x, or is less than this by an even number. So here's a little example. Notice that here you start from left to right. It goes from a plus to a minus. So that's one sign change. Then it goes from a negative to a plus. That's a second sign change. And then it goes from a plus to a minus. That's 3 sign changes. So that is what it determines here is when you have a polynomial that has real coefficients, and that's equal to the number of coefficients of variations, I should say, in signs occurring here. That's just an example there. Some more examples you have here. Notice the relationship in the table. You have positive real zeros, 3 negative real zeros, 0 imaginary zeros, so total zeros is 6. And that is all I have time for, but I just wanted to give you a taste of what we do at City Tutoring. And these are just some of the exercises. I also give them sometimes, the option of, because I know that in their schools, they do graphing, and that's fine too. But it's not really my focus. But let me know in the comment section if this is familiar to you. Let me know if they're going over this in your school. If they're not, then I hope this video was helpful to you. You need to research these theorems. Have a great night, everyone. I hope you are all blessed. And hopefully tomorrow is the Lord's Day, Sunday. I will have a little Sunday message for everyone about things in life. Thank you all.